3, part 1. Here we go. Properties of a definite integral. We made it through the limit definition, you guys, so we're on the up and up. All right, properties of a definite integral. All right, so use your TI to compute the following. Let's do math 9 of x squared comma x comma 0 comma 3. Okay, get 9. All right, so that's 9. And now what happens if this is the lower bound, 0 to 3. So you're accumulating area left to right as you would read. What happens if we accumulate area in the other direction from right to left? So math. I just hit second, sorry. Math 9, x squared comma x comma 3 to 0. Let's accumulate in the opposite direction. And we get negative 9. So what does this suggest? This suggests that if you have the integral from 3 to 0, x squared here, it is opposite, okay? It's opposite of, this is sort of the comfortable integral, so if it's uncomfortable, it's equal, to the opposite. It really kind of makes more sense to me to write the normal way is equal. If you go kind of right to left, these are not equal. That's equal. Okay. All right. So properties of a definite integral. So the first one here, recall here is the limit of a Riemann sum definition right here, and so this will also show you why that occurs. I think this will be nice to kind of understand instead of saying left to right, right to left, why this occurs. And it occurs right here on this delta x. Remember, this is the upper bound minus the lower bound over n, okay? So this is why this property up here occurs. Okay, so delta x is b minus a over n, okay? And if we moved from left to right, across the interval, you get b minus a over n. But what would happen if we integrated in the opposite direction? Okay, this time it would be a minus b over n. And if we pulled that negative out, that's the same thing as negative b minus a over n. So there you go. That's where it comes from. All right, and we'll just scale that right on out there. Okay, and so here's the formal kind of conclusion, I guess. Okay, so there's that integral is equal to itself. What happens if I flip it? It gets negated. Okay. So that is our first property down here, the order of integration. All right. So I have to switch the order of integration. That will negate the integral. Okay. All right. Next little piece here. What do you think would happen if I integrated from a to a of a function with regards to x? Okay, so, let's say I'm integrating from a to a. What is the area under this curve? Well, we haven't gone laterally any distance, so this is going to be 0. Okay, so that's a 0 property there. We've done quite a bit with this already. We can take out a scalar multiple, just to get it out of your way. And it has to be, make sure you don't scale out a variable. This is a coefficient. Don't scale out anything that can be integrated. So take a k out there. A special case here is a negative. You can, I don't, you know, this really isn't a special case. It's just, don't confuse this with this, okay? Don't confuse these two. You're just factoring out a constant here. And this, you know, a coefficient, I'd rather call it a coefficient. But you're just factoring out here, you know, a -1. And so I'm sure this negates the integral as well, sure, but the bounds don't change. Sure, that negates the integral, but it doesn't change these bounds here. When when you change the bounds, it negates the integral. When you factor out a -1, it negates the integral, but the bounds don't change, okay? And then the last thing here is I can split this. You can just do AB, f of x dx. So the integral of a sum or a difference is the same as the sum and difference of these integrals. That's pretty easy. I got that all in there. All right, so this is just negative. Let's do this. I think I just mostly like to use my erasable pen. Okay, so sorry, I didn't fill this in. So since the width of this region is 0, then the area is 0, therefore a 0. That's our number 2. You know, there's the dx is 0, so that's going to multiply to 0. All right, next page here. What do we have? Okay. Another property, use color to draw in the area of the curve from A to C using a different color. Okay, so A to C is here. You know, different color. C to B is here. All right. The sum of the areas of under the curve is the same as the area from A to B. So if you need to split integrals, you can. If you need to put them together, back together, you can. So A to B is the same thing as A to C, and then C to B. And that'll come in handy. If, say, this function, say like on a piecewise or something, say if this function is something and this function is something else. It's continuous, but you may have to integrate this function differently than this function if they're defined differently. So this just is giving us permission to do that. And that's just number 5 down here. I can go to A to some C, and then go from that C on to B. And that's the same area under the curve. It's just a number. As long as you split somewhere in the middle and add them up, you get the same number. These are pretty easy. On the graph, draw a rectangle over this interval, A to B, with the height that corresponds to the minimum value of f. Okay, the area of this rectangle is, so where's the lowest value? Right here. The minimum, this would be f min. All right, and then this is the highest part. Okay, so, you know, the area of this rectangle is going to be f minimum of B minus A. Okay, well that's obviously, you know, less than the area under the curve. Here's the area under the curve. All of this is the area under the curve. Well, from the minimum point and down to the x-axis, that's less than the exact area. If we do a second rectangle from the max, draw this rectangle. Okay, so that's going to be f max times B minus A. Okay, and so that would obviously be all that area would be greater than the blue. So this is a kind of an approximation method if you can't integrate and get exact, but you could calculate rectangles. So you know that f min B minus A is here, and f max, the max lowest point on the graph times the dx, or the interval length, and the highest point here times the interval length. You know the exact area is somewhere between those. All right, so that's the max-min inequality. And it's just a way to get an estimate. This isn't a huge deal, but just a way to get an estimate there. Sort of another kind of common sense type thing here. Suppose f of x is higher than g of x. Okay. Shade the area under the curve of f. And shade the area under the curve of g. All right. So the area under the curve of f, if it's greater than or equal to g, if f is greater than or equal to g, then the area under the curve will be greater than or equal to g. I mean, hopefully that makes sense. It's called the domination little property. Okay, so let's fill this in. Estimate the lowest point on the graph times the interval length. That rectangle is just a rectangle. Max, I think I put this as max, b minus a. That's just a rectangle. So this minimum rectangle, maximum rectangle, the integral will be somewhere between those. And then if f of x is greater than g of x on a or b, then the integral, this just means the exact area on the curve will be as well. If f dominates here, f will dominate here. The special case is if f is non-negative. So if the function is non-negative, if the function is above the x-axis, then it will have an area greater than 0. All right. So that's all pretty easy. Let's do some problems. Problems are fun. Okay, so we're going to show some use of the properties. So here they're giving us some givens. All right. So we know from 1 to 8 we're 11, and from 1 to 3 we are. We've got to look at the function names. So f from 1 to 8 is 11. F from 1 to 3 is 7. And then h from 1 to 3 is 5. So find the following integrals. Well, this is just the given. This is matching the given right here. Okay, so this is just the integral from 1 to 3, h t dt. Well, that's the given. But the variable changed, okay? But the variable changed. Guess what? It doesn't matter. Okay, the variable doesn't matter. It doesn't matter if we've got x, x on the x-axis or time. The variable doesn't change. The number doesn't change if the variable changes. So you could just think of that as that. The only change there was the variable changing. No big deal. We mentioned that earlier in class. All right, let's go from 1 to 8 of f of x. All right, 8 to 1. So here's a property. So we've got this given, that's 11. And so this is going to be the negative, okay? This is going to be the negative of 1 to 8 f of x dx. So this is going to be equal to negative 11. Okay, it's property here. You can just use different variables. No big deal. Can't do different function names, but you can use different variables. Here, the bounds are kind of uncomfortable here. So if you make them comfortable in a left to right movement, it'll be the opposite. 4 to 4. We're covering no ground here. This is just 0. And then 1 to 4 here of f of x. Let's see. So I know what I'm going from 1 to 3. I know 1 to 8. So I could probably figure out 3 to 5. Okay? But 1 to 4, this is not enough info, and that's okay. Sometimes that happens. Okay? But now 3 to 8 I can do. So I know all the way, whatever this is. We're going from 1 to 8. Let's just do a hypothetical something. Some curve. I don't know. So down and down. So I know that all of this is 11. And I know from 1 to 3 is 7. So I can compute that the rest of this is going to be 4. So 2 approaches. I don't really think we need 2 approaches here. I think we could just kind of say 1 to 8 of f of x dx is equal to 1 to 3 of f of x dx plus 3 to 8 of f of x dx. So this is what 11 equals 7 plus some unknown 4 equals, I'm just letting, let x equal this, and then we'll just write it properly. Or if I wanted to say x equal 4, I would have had to say let x equal this integral. All right, so that's pretty easy. And then our last one here, I think is just going to have 1 to 3, 1 to 3 of f, good. 1 to 3 of h, that's all good. So I'm going to split this, scale it out. Okay, so this is a given, and this is a given. So 7 minus 10, that's negative 3. All right, next problem. Down below here. All right, so we've got a value from 1 to 3 of x squared is 26 over 3, and then given value of x from 1 to 3 is just 4, and a given value from 1 to 3 of just dx is 2. So let's find the integral of this polynomial. So let's split it. Scale it there. Well, let's do it all the same. All right, 1 to 3, 5x minus 1 to 3, 7. So I need to close my integrals here. Dx, dx, and dx. Close each individual integral. Okay, so let's scale out the negative sign. Let's scale out the 5. And let's scale out the 7. Okay, so this is going to be negative 26 over 3. This is going to be 4. So this is just given right here, right? This piece was just given. This piece was just given up above. And just the integral, and this is just a 1 right here. That's 2. All right, so we've got a negative here. Sorry. Okay, so we've got negative 26 over 3 plus 20 minus 14. All right, so we've got, what's 18 over 3, that's the 6. Minus 26 over 3, so negative 8 over 3. All right. Yep, that was a minus, that's a minus, that's a minus. Okay, use the Max-Min theory to estimate. So in terms of this graph, let's look at 0. Anything to the 0 power is 1, so the graph will be at 0, 1. And if I put 1 in here, e to the negative 1 will be 1 over e, so 1, that'll be 1 over e. Okay, so e to the negative 1 is just 1 over e. Okay, so, whatever's happening here, this curve. Area under, so analyze and sketch. We don't need our TI here, we got 0, 1. All right, which came from e to the 0, and then 1 and 1 over e. So I can estimate that. I know the exact area under this curve will be this lowest point. That's the minimum y value. Times the length. So that would be this rectangle right here. So that area is going to be less than the area under the curve. And then the max rectangle would be a 1 by 1. So I know the exact area under this curve is somewhere between 1 over e and 1. Okay, let's jam through this next page. This is just a warm-up. Just go through this warm-up. So some derivatives, just to remind us that we still have those in our life, and that when we on the antiderivative, we go backwards. All right, so that is x to the 5th, so 5x to the 4th. And I mean, there'll be times where your brain is going forward and backward and forward and backward on the AP exam, going, am I integrating, am I differentiating, what's going on? So you just kind of have to, but let the notation, that's how we're so big on notation, let the notation kind of trigger what you're supposed to do in your brain. So ddx, this is 5x to the 4, and then that's just 0. Remember, this is 1 over 2 of the root times the chain, okay? Times the chain, so then you can do a little simplification there. 2 over 4x plus 5 under the root is 3. The derivative of cosine is negative sine of x. I mean, don't you now feel like writing like a plus c here? But don't do that on derivatives. This is secant square. Cosecant here is negative cosecant x cotan x. Okay. Oh gosh, remember this one? 1 over 1 minus x squared. Be taking those backwards later. 1 plus x squared, or the other way, x squared plus 1 doesn't matter. This one, you get that absolute value in front, and then it's x squared minus 1. Okay, and those are your inverse trig functions. Okay, looks good. Your easiest one of all here is e to the 5x times the chain. Remember, this one is kind of the same as this one. E to the 5x is just e to the 5x times the chain, but really times ln of e, which you don't need to write because it's 1. So you can use that to help you here. This is just write it down, ln of 7. And then ln here, 1 over x minus 3. X needs to be greater than 3 here. And then times the chain of 1, so we don't write that. All right, so let's find some general antiderivatives. General, so that's plus c. Okay, so now we raise the exponent by 1, multiply by the reciprocal, and sine integrates to negative cosine plus c. All right, next one. 7 just integrates up to 7x plus c. And then this one here, okay? So this one, you've got to, if you have a power, what I would encourage is that you might be thinking, let's just bring this up, okay? And then what happens when I raise that exponent by 1, and you multiply by the reciprocal, that's out, so that's undefined, okay? So if you were thinking of bringing this up, and then you raise it by 1, that's 0, and divide by 0, that's no bueno. So let your brain say, okay, there's something else that happens here. And what happens here is that this is the antiderivative here is ln. Okay, that's the ln. You can just bring 4 out in front of this x plus 3 plus c. Okay, and so what we're going to be doing here is this domain here is x has to be greater than negative 3. So we're kind of learning about this ln here, this ln of x. All right. And we're going to formalize that here on the bottom, but maybe I'll come back to 17. Let's leave it as this right now. All right. So little discovery activity. Okay. So if you have f is equal to ln of absolute value x, so this has to be positive, right, behind the ln. This has to be a positive number. So this is greater, or, can't, domain restriction, we don't really need, since I've got the absolute value in there, the only thing I just need to get rid of is can't equal to 0. If it were just ln of x, we would say positive, but we've got that built in, and so all I need to add here is x can equal to 0. So if I were to write this as a piecewise, this equals x for x greater than or equal to 0. Okay? But I've already thrown that out. So, and this equals negative x for x less than 0. So that is here. You know, we have this in review. I guess this isn't part of this problem. That's just a review. So let's just be good and put that there. So if I'm doing the derivative of the ln of x, right, I'm getting 1 over x. And if I'm doing the derivative of ln of x, okay, and, you know, we know that this x is less than 0 here, and we can't have that just as is, but this is coming from, you know, this particular situation with absolute value built into the original function. So we can have this because it's stemming from this. So this would come out to be the 1 over x times the chain of negative 1. Okay, so that's 1 over x negative 1 because you know, x is negative. All right, and so let's look at on our calculator here. It says use your calculator to graph 1 over ln. Oops. Sorry. I was jumping down here. Check graphically. Use your TI to graph ln of absolute value of x. All right. Okay, so let's do a zoom 6. Okay, there we go. Okay, so let's put that on our graph here. And yeah, this is negative 1 and 1. Okay, so the absolute value, you're just able to get the ln, you know, over to the other side. And then if you were to graph that derivative, you're going to get math 8 of the ln of math over abs x in that, comma x in that parentheses. Okay, so I'm graphing the derivative of ln of the absolute value of x. All right, graph. That's good. Uh-oh. Doesn't like me. What happened here? Why doesn't it like me? Because I am missing a parenthesis. All right, got to close the absolute value here as well. Calculator will tell you what it doesn't like. Okay, let's try that, and let's actually take this one off. All right, there we go. So that derivative is graphing that just like so. Okay, so what does this have to do with anything? So when you are integrating 1 over x, okay, 1 over x. Okay, so this is the graph of, right here is the graph of 1 over x. We all know that, hopefully. And this is also the graph of, you know, the derivative of ln of absolute value of x. Same graph. So this is the derivative of ln of x, absolute value of x. And this is the derivative of 1 over x. Okay. So when I am taking the antiderivative of 1 over x, I can't just say ln of x. Okay, because the ln of x is just this graph right here. And this graph does not translate to this graph. This graph translates to this graph. So we have to do the ln of absolute value. So it's something to remember. This is just 1 over x. Here, x can equal 0. But over here, when you integrate, you have to integrate up. You know, ddx of absolute value of x is just 1 over x. That's fine. And when you integrate it up, you have to... I just always think to myself, I just need to protect what's behind the logarithm. Make sure it's positive. That's the easiest way for me to remember it. This may be, you know, too much information. So when you integrate ln when you integrate 1 over x to ln, just protect it in absolute values. And this is why. We know what this graph looks like. That is also the graph of here, because the graph of the absolute value, you know, it behind the logarithm. So we just have to make sure everything cooperates with one another. And that's another one of those things that's kind of out there. All right, so that's the end of 6.3, part 1. All right. Bye, guys.